Good morning, students. Okay, today I will explain to you next third part here, hydrocarbons third part. Okay, hydrocarbons part 3. Here already we discussed the preparation of alkenes. Today we'll discuss about what is that physical properties. The physical properties in that physical properties, in the first case, what is that? The first four alkanes. In this first four alkanes, that means methane to butane are colorless and waterless gases. Colorless and waterless gases. Next 13, okay, that means from pentane to heptadecane are colorless and waterless liquids. That means 1 to 4 are gases. C5 to C17 are liquids, and above more than the rest of the higher alkanes, that means 18 above, are colorless solids at ordinary temperature. Colorless solids at ordinary temperature. So C1 to C4 gases. Okay, C5 to C17, these are liquids, and okay, C18 and plus, those are solids. Those are solids, colorless solids. This is one point. And next one is alkanes. Next is, what is that? Alkanes being what are those here? Non-polar molecules. Alkanes are non-polar molecules. Why mean that alkane bond found between carbon-carbon. So between same atoms bond is forming means no electron negative difference. So that's why those are non-polar molecules. So we know that like dissolves like. We know that what is that? Okay, like dissolves like dissolves like means what is that? So polar substance soluble in polar solvents, non-polar substance soluble in non-polar solvents. Like that, alkanes are having non-polar nature, so these are soluble in non-polar solvents like benzene, ether, and chloroform. Like benzene, ether, and chloroform. However, they are insoluble in polar solvents like water. Okay, soluble in polar solvents like benzene, ether, chloroform. Insoluble in polar solvents like water. Okay, and their solubility decreases with increase in molecular weight. Their solubility decreases with increase in molecular weight. Understand? Molecular weight increases, solubility decreases. Next, melting and boiling points are increases with molecular mass. Huh? So melting and boiling points. This one, if you take it, melting and boiling points are increases with molecular mass and decreases with number of branches. Number of branches increases, boiling point, melting point decreases, and molecular mass, that means number of carbon atoms increases, melting point, boiling point increases. Okay, so next point. And next, if you take it here, melting point. The melting point, while taking that melting point, in this case, okay, even number and odd number. Here, even number of carbon atoms are there. Here, odd number of carbon atoms are there. So, whenever you're taking even number, sorry, odd number, both the terminal groups are, terminal carbons are one side are there. That's why another group is coming to this one, like this new group is coming. Okay, this group and here this group, between these repulsions will arise. That's why less close packing. Melting point, how can we explain? It is based on close packing, based on close packing. So another new group is coming like this, another pentane is coming like that. So this terminal group, both are same side. So repulsions will arise, less close packing will be there. Like this, here less close packing, less close packing will be there, and even number when you are taking, so terminal groups opposite to each other. Terminal groups opposite to each other. So when another group is entering like that, what is happening then? So like this. So these terminal groups opposite side are there. That's why here, whenever you're taking this one, there you can get more close packing. In this case, what you can get it here, more close packing will be there. More close packing. Understand, students? So less close packing, more close packing, we can get it. So that's why even number of any compound alkanes, if it is contain even number of carbons, okay, it's having higher melting point than odd number of carbon atoms. Odd number of carbon atoms. Okay, students. Next, boiling point decreases with the increase of branches. Number of branches increases, boiling point increases. Reason, okay, I will give one example. So if you take it this one, it is N-pentane and this one is neopentane. Okay, so this is N-pentane. N-pentane having higher boiling point than neopentane. N-pentane having higher boiling point than neopentane. Why it is having higher boiling point and that is having lower boiling point means when it is having long chain, okay, so surface area, what is that, higher will be there. That means due to increase in branching, that means neopentane, about here neopentane is gas and neo normal pentane is liquid, that only. N-pentane is liquid, neopentane is gas due to increase in branching. In that neopentane branches are there. That's why here surface area, in the surface area less will be there. Here less branches, surface area more. And more surface area means intermolecular forces are more, van der Waals attractions are more will be there. More surface area means more surface area. Here due to branches, intermolecular forces and van der Waals forces of attractions are very less will be there. That's why neopentane is gas, N-pentane is liquid. So physical state if you see, okay, here alkane C1 to C4 gaseous state and C5 to C17 liquid state except neopentane. Actually, C5 means C5 to C17 what we discuss. C5 to C17 are liquids, but due to more branches in neopentane, it is showing neopentane showing gaseous state. C18 and above are solids, colorless solids like wax, and alkanes are lighter than water. So it's float over water. Okay, alkanes are lighter than water. That means they may have higher molecular weight, but there is no hydrogen bond. That's why, okay, no hydrogen bond in alkanes. So alkanes are lighter than water. Alkanes are lighter than water. Okay, so like this we can discuss. Now, up to now, what we discuss, those are physical properties. Now we'll discuss about chemical properties. Chemical properties while discussing, the first important thing is chemical properties while discussing first important halogenation plays very important role. Okay, in that alkanes here, alkanes halogenation means, so while discussing about reactivity, so reactivity of halogens following order like this will be there. F2, Cl2, Br2, I2. Here, F2 is highly reactive here. When fluorine is reacting with alkanes, When fluorine is reacting with alkane, that is explosive reaction. Not only with alkane, any substance that much highly reactive is fluorine. And Cl2 is little bit less reactive than fluorine, and Br2 is very less reactive than fluorine, and I2 is very less reactive. Huh? So that reactivity order of halogens follows the order. Ft is very greater than Cl2, Cl2 greater than Br2, Br2 greater than I2. So F2 participate chemical reaction F2, we no need to produce any energy. Dark medium, very low temperature also, fluorine can participate in chemical reaction. So to participate in chemical reaction, for chlorine and bromine, we have to supply higher temperature. That means in the presence of light, ultraviolet radiations, no light means in the dark medium, high temperature we have to provide. So halogenation of alkenes is, it is free radical mechanism. That one is free radical mechanism, nucleophilic, free radical substitution reaction. Okay, halogenation of alkenes is what is that? Free radical substitution reaction. Free radical, that one is free radical substitution reaction. It is example for free radical substitution reaction. Okay, so this one you can take it. Here, when you are taking this one, CH4, when it is reacting with chlorine in the presence of light, H mu means light energy. E is equal to H mu. Atomic structure lesson we learn. So light energy. So light energy means generally ultraviolet radiation will take it. So CH4 and Cl2 in the presence of light energy, there you are getting methyl chloride you are getting. That methyl chloride, when it is reacting with chlorine gas, dichloromethane, once again reacting with chlorine in the presence of light, trichloromethane, and once again means tetrachloromethane, like that we are getting. This is example of what is that here? Free radical substitution reaction. And bromine also like this only we will get it. Chlorine, bromine. In that chlorine, bromine, which is more reactive here? Cl2 is more reactive than bromine. And next, here see once here what is given in the C. Direct fluorination is explosive. That's why indirect method will follow. Inorganic fluorides on bromo or ido derivatives. This is reaction is example of the halogen exchange reaction. Schwarz reaction. Already, okay, Schwarz second year students who are preparing for long term and NEET exams, those students, haloalkanes, halogens, that lesson you prepare. Schwarz reaction. The Schwarz reaction, in the Schwarz reaction, silver fluoride or mercury fluoride we can use. Okay, here ethyl bromide. So here what is a halogen exchange reaction? This is what is that halogen exchange reaction. Here Br is replaced by fluorine. So like that ethyl fluoride and mercury bromide we are getting. This reaction is example for halogen exchange reaction. Halogen exchange reaction. Halogen exchange reaction. Bromine is slower than chlorine and carried out at high temperature. That means to participate chemical reaction comparatively chlorine, bromine require little bit high temperature. But iodine is reversible reaction. But iodine is reversible reaction. That means alkane when it is reacting with I2, their methyl iodide, like this methyl iodide plus hydrogen iodide is forming. Okay, but it is what is that? Reversible reaction. But this one is reversible reaction. That means, okay, reactants convert into products, products also convert into reactant. In that case, we must use catalyst. We must use catalyst here. Catalyst is what is that? HiO3. Okay, when you add HiO3, what is happening? That HiO3 is reacting with product like HI. So HI and HiO3, when those two are reacting each other, there we are getting I2 plus water. I2 plus what we're getting. That means I2 is forming means which concentration is increasing. So reactant concentration. According to Le Chatelier principle, at equilibrium, reactant concentration increases means equilibrium shift to forward direction. Equilibrium shift to forward direction. So that way we can get for methane and I2 in the presence of HiO3, what will get it? Iodomethane will get it in the presence of catalyst. Okay, but generally to prepare alkyl iodides, we'll use halogen exchange reaction like fluoroethane, like fluoroethane. That reaction is called Finkelstein reaction. That reaction is called Finkelstein reaction. In this case, alkyl halide like chlorides and bromides, when those are reacting with sodium iodide in the presence of acetone, their alkyl iodide and sodium chlorides we can get it. Sodium chloride we are getting by using this is what is that example for halogen exchange reaction. Halogen exchange reaction. It is also Finkelstein reaction. Haloalkenes, halorines. You will learn halogen exchange reaction. Hmm. So we cannot prepare by using Finkelstein reaction. We cannot prepare what is that alkyl chloride and alkyl bromide. Why means sodium chloride, sodium bromides not soluble in acetone. Here to takes place ionic reactions, how we require water as solvent. To takes place organic reactions, we require organic solvents required. So organic solvents here they're taking acetone. So sodium iodide. Due to large size of iodine, it's getting covalent nature. Sodium iodide getting covalent nature. Covalent sodium iodide soluble in acetone. Why means covalent nature substance which is having covalent nature slightly get non-polar nature according to like dissolves like sodium iodide is soluble in acetone. So that way it participates in chemical reaction. But to prepare the alkyl chloride and alkyl bromide, there we have to take it sodium chloride and sodium bromide. Whenever you are taking sodium chlorides and sodium bromide, these are not soluble in acetone because of their ionic nature. That's why, okay, by using Finkelstein reaction, we cannot prepare alkyl chloride and alkyl bromides. Okay, students, understand? So this, it is also very, very important point. Next, and halogenation, it is free radical mechanism. Yeah, this one is free radical mechanism. So in this, if you see that this one is free radical mechanism, free radical mechanism. In this mechanism, three steps will be there. Chain, first one is what is the chain initiation step. Second one is chain propagation step. Last one is chain termination. Chain initiation step means initial step what is happening. Chain propagation step means continuous. That means that step continuously takes place like cyclic process. And chain termination step means end of that reaction. End of that reaction. And very important point, in the presence of light, free radicals will be formed. So like that halogen, whenever you're taking in the presence of temperature or ultraviolet radiation, so between here like this, X bond X, this bond is undergoing homolytic cleavage and it's giving free radicals and it's giving free radicals like this. So in the chain propagation step, that free radical, okay, alkane is there. Very, very important point. What is that? Free radical, anywhere free radical is there means that free radical initiates other bonds to undergo homolytic cleavage. To undergo homolytic cleavage. Like that, in the presence of this free radical, this bond will undergo homolytic cleavage and there you will get it free radicals like this. There what you are getting there, what will get it R bond X, sorry, R bond R radical plus HX will get it. R radical plus HX. This R radical, okay, initiates once again halogen bond, X bond X. So homolytic cleavage there, okay, like this homolytic cleavage takes place. And there what you are getting that, so there you will get it R bond X plus X radical like that. So once again we got it X radical. This X radical once again it will go here and initiates alkane, and R radical HX hydrogen halide will form. This R radical once again initiates halogen. Like that this is continuously takes place. That's why this step is called chain propagation step. So continuously, this one will form. This is initiating these bonds. A radical is forming. This radical initiates this halide, and alkyl halide plus this one you are getting. Next, end step, chain termination step. End of the reaction is what is happening. All free radicals combine together and giving molecules. Okay, if you stop production of free radicals, the reaction will be stopped. So all free radicals combine together giving molecules mean that is chain termination step. Here free radicals means X radical, X radical. These two combine together, then what will get it? Halogen. Next, X radical and alkyl radical. These two combine together, what you will get it? Alkyl halide. Next, R radical and R radical. These two combine together and there what you are getting? Alkane we are getting. Like that, here what is it here? This is initiation step. This one is initiation step and this one is propagation step. This one is what is that? Propagation step. And these three are what is that? Chain termination step. Chain termination step. Okay, students, understand? So, like that, it is halogenation. Okay, that means chain initiation step, chain propagation step, chain termination step. And here one point is given, one thing, chain inhibitors stop chain propagation by reacting with free radical intermediates. That means here peroxy linkage if you take it, O2, okay, peroxy radical, O bond O, okay, this one if you take it like this, O, so what is it? O bond O, radical radical. So this R radical, when it is reactive peroxy radical, so one other peroxy alkyl radical will form. That one stops further reaction. Chain inhibitor stops chain propagation by reacting with free radical intermediates. Reacting free radical intermediates. Understand? So this next nitration. Nitration, if you take in that nitration, what's happening? So just NO2 group. Okay, NO2 group reacting with alkane, and there we are getting that. For example, if you take in propane, when it is undergoing nitration, there nitropropane. What you are getting that? There we got it nitropropane. What you got it? Nitropropane to nitropropane, nitropropane to nitropropane, and next one is nitroethane. Next one is nitroethane. After that, nitromethane. After that, what is that here? Nitromethane. Like that, compounds are forming. So main compounds we can take these two: 2 nitropropane, nitropropane. Okay, students. Next, sulfonation. Sulfonation means what is that? Nitration means nitric acid is reacting with alkane. Like that, sulfonation means here what is that? Um, Hydrogen is replaced by sulfonic acid. So main reaction we can take like this. This reaction we can take it this way. Rate of sulfonation means here mostly tertiary alkanes. Generally, we discussed already. Alkanes are less reactive. Alkanes are less reactive. Here, reactivity order, if you see the rate of tertiary, secondary, primary is given. Tertiary alkanes, tertiary alkanes, when those are reacting H2SO4, what is happening there? Here, this H and H2SO4 OH. So there we will get it H2O is coming out. So tertiary butyl sulfonic acid we are getting. Which compound we are getting? Tertiary tertiary butyl sulfonic acid we got it. Sulfonic acid. Like that, nitration and sulfonation both are substitution reactions. Both are what are those? Substitution reaction. The rate of sulfonation means tertiary alkanes are highly reactive than secondary. Secondary alkanes are highly reactive than primary. Next, chlorosulfonation. Okay, chlorosulfonation means alkanes react with sulfur dioxide and chlorine. This reaction is also called Reed's reaction. It is also called Reed's reaction. In this, see once, alkane. This alkane, when it is propane, when it is reactive with SO2 in the presence of chlorine, okay, here ultraviolet radiation, what is happening means that hydrogen is replaced by sulfonyl chloride. So what you got is compound propyl sulfonyl chloride. What you got it? Here we are getting the substance name is propyl sulfonyl chloride. We got it. This reaction is called Reed's reaction. Propyl sulfonyl chloride. So where we'll use what is the use of this reagent mean? This process is used in the commercial formation of detergents. So to prepare detergents, we are using this one. Hmm. Reed's reaction. Reed's reaction. In this case, here total how many carbons are there? 13 carbons are there. Total here 1, here 10, here 2. Total 13. See 13 carbons, this long chain, when it is reacting with SO2 and Cl2, what you got it here? Okay, sulfonyl chloride. When it is reacting with NaOH, okay, alkaline hydrolysis, there you are getting that long chain. One long chain. Actually, it is dodecyl sulfonyl chloride here. Okay, here one extra carbon they put. So sodium salt of sulfonic acid. So like that long detergents means it those contain long chains. Detergents means those contain long chain carbons. So like that sodium salts of sulfonic acids we are prepared. Okay, so this. Next, isomerization. Isomerization whenever you're taking. In this isomerization, very simple here, long chains we are taking. When N-butane, N-pentane, N-hexane, when you take in, those will undergo isomerization. That means those compounds in the presence of one particular reagent, it gives their chain isomers. Chain isomer. I will show you. See once here AlCl3 is isomerization agent. AlCl3. In the presence of these, what is happening means N-butane is converted into isobutane. That means it's chain isomer. And N-heptane is converted into 2, 2, 3 trimethylbutane. Like that, it's chain isomer. Like that, it's converted. N-octane is converted into isooctane. Then octane is converted into isooctane. That means in the branch chains we are getting. Like that, okay, long chains to convert it into branched chains. That means same number, same molecular formula. Long chains to convert it into branched chains. Okay, which reagent we require here? Aluminum trichloride and high temperature. This method is called isomerization. This one is called isomerization. Okay, students. Okay, so in this, N-butane converted into isobutane, N-heptane is converted into, so it's isomer. 2 comma 2 comma 3 trimethylbutane or any other chain isomer also we can take it. N-octane is converted into, N-octane is converted into isooctane. Iso. Iso means like this group anywhere is there means that one we can call iso. Okay, so this one here. Okay, this type of reactions where we are using also down is given. See, this reaction is used in petroleum industries. Petroleum industries. We can convert unbranched alkenes to branched alkanes. Branched alkanes. So here are bad fuel to good fuel. That means branched alkanes are good fuel and unbranched alkanes are okay. Those are not that much good fuel. Okay. So this one here and this is about isomerization. This is about isomerization. Next, combustion. Combustion, if you take it, combustion means so many cases we learn that one. Combustion means what is the hydrocarbon when it is reacting with the oxygen. Okay, in the again when it is reacting with oxygen, there carbon dioxide, water, heat, and lights are produced. That reactions are called combustion. Those reactions are called combustions. So now I am giving one example here. So CH4, methane when you take in, CH4 when it is undergoing combustion, okay, there you can get it. One carbon is there, so one carbon dioxide. Four hydrogens means two H2O will get it. Two H2O. And total product side, how many oxygen atoms are there? 2 plus 2, 4 are there. So in front of oxygen, you have to put 2 water. So like that, it is a combustion balance reaction. Combustion balance reaction. So generally, okay, CXHY if you take it, here CXHY whenever you're taking, so X number of carbon dioxide, Y by 2 number of water molecules will form. X number of carbon dioxide, Y by 2 number of water molecules will form. So how to write that balanced equation mean X plus Y by 4 oxygen molecules. You must have idea on this one. You must have idea on this equation here, this one. Okay. So this reaction here, so like this, it is combustion reaction. So combustion reaction means hydrocarbon when it is burning in the presence of oxygen, carbon dioxide, water, light, and okay, sound also will produce. Light, heat, light energy, heat energy, and sound also sometimes produces. Those reactions are called combustion reactions. Okay, next, aromatization. Aromatization means generally compounds which contain okay benzene ring. Okay, those follows Huckel rules. Aromaticity. For that classes I will explain. 4n plus 2 pi electron. That one is called aromatic compounds. So here what we are doing mean. So we are taking that saturated alkenes. That means N-hexane, N-heptane, N-octane. So in the presence of aromatic okay agent, aromatization agent mean here what we are taking that chromium trioxide, aluminum oxide in the presence of heat. N-hexane is converted to benzene. That means N-hexane means how many carbons will be there? 6 carbons. N-hexane means 6 carbons will be there. So when that N-hexane undergoing aromatization, okay, aromatic agent means chromium trioxide, aluminum oxide, heat we did, benzene we are getting, C6H6 we are getting. So N-heptane means how many carbons will be there? 7 carbons. N-heptane means Okay, 7 carbons will be there. So these 7 carbons, when those are undergoing aromatization, what is happening? Okay, toluene. This substance is called toluene. Toluene we are getting. Here we got it benzene, and second case toluene we are getting. N-octane. The N-octane means 8 carbons. N-octane means 8 carbons when you take it. When 8 carbons, when those are undergoing aromatization, orthodimethylbenzene, metadimethylbenzene, paradimethylbenzene, those are called xylenes. I will give those structures like this. Here CH3 and CH3, orthodimethylbenzene. Okay, these all are called xylenes. And next, here CH3 and meta position also CH3, metadimethylbenzene. And next one is here like this, methyl group and methyl group, paradimethylbenzene. Paradimethylbenzene. Like that, these are, it is orthodimethylbenzene, meta dimethylbenzene, this is para-dimethyl. These are called xylene, orthoxylene, metaxylene, paraxylene. Okay, students. So this it is called aromatization, and 21 and recent mains exams. This question was given aromaticity related. And next, cracking and hydrocracking. Cracking and hydrocracking is very simple here. One bigger molecule, when it is converted to simple molecule, that is called cracking, or pyrolysis also we can call. Cracking or hmm, pyrolysis by heating. When we are heating the substance, one bigger molecule is converted into simple molecules. Now, if you see here, one long chain contain 12 carbons. Okay, long chain contain 12 carbons. Whenever we are heating in the presence of catalyst, here what we got in 5 carbons and 7 carbons, like that. Short carbon chains formed, and this is called cracking or pyrolysis. So here 12 carbons are there. When you heat that one, here what is that? C5H10 and C7H16. Like that, you may get alkanes or alkenes also sometimes you'll get. Like that, one bigger molecule is converted into simple molecule in the presence of high temperature. In the presence of high temperature, that one is called cracking. That one is called cracking. If we use hydrocracking, means hydrogen is added to give saturated hydrocarbons. Hydrocracking means in hydrocracking, hydrogen is added to give saturated hydrocarbon. This one is called cracking. Okay, students. So cracking is bigger molecule is converted into simple molecule. So this is called cracking or pyrolysis. Now we'll discuss some solved examples. Now we'll discuss some solved examples. We'll discuss the reaction conditions leads to the best yields of ethyl chloride are. So to get ethyl chloride, which alkane react with the halogen in the presence of sunlight means that is excess of alkane. Okay, what we have to take it this one. Excess of alkane when it is react with chlorine in the presence of sunlight, there you can get it ethyl chloride. What you can get it? Ethyl chloride, best yield, good yield, more quantity you can get it. More quantity. Okay, so this one. Next, okay, ethane SO2 Cl2 in the presence of light. Okay, this reaction is what is that here? Already we learned Reed's reaction. This is what is that? Reed's reaction. There, alkyl sulfonyl chloride we are getting. Alkyl sulfonyl chloride. We discussed already. Reed's reaction. Huh? And product of the Wolff-Kishner reduction. Wolff-Kishner reduction, what is happening? Carbonyl groups are converted into alkanes. What's happening? Carbonyl groups are converted into alkanes in the presence of hydrazine. In the presence of hydrazine and KOH and ethylene glycol. Ethylene glycol. Okay, so like that we got it, ethylene glycol. So this is called Wolff-Kishner reduction. By using Wolff-Kishner reduction, what we are able to prepare here? Alkanes. Here, carbonyl groups convert into alkanes. Next question is, which of the following should be subjected to Wurtz reaction to obtain best yield of N-hexane? Best yield of N-hexane. And very important point, by using Wurtz reaction, we can prepare only symmetrical alkanes. N-hexane meaning what is that? If you take N-hexane, C bond, C bond, C bond, C bond, okay, like this is there. So symmetrical alkane, this given one is symmetrical alkane means we can cut this one into two equal parts. Why means given one is it is a symmetrical alkane. By using Wurtz reaction, we can prepare symmetrical alkane. Given one is N-hexane is symmetrical alkane. So if you break it here to equal parts, here if you break it here, if you can put here one halogen, here one halogen. That means we got this substance, we got that alkane from what is that propyl chloride, N propyl halide, okay, propyl halide. When it is undergoing Wurtz reaction in the presence of sodium metal and dry ether, there you can get N-hexane. So what is answer here? Their answer, you can take it C option, N-propyl bromide. C option is right answer. Okay, remaining all are, what are those? Here remaining all are ethyl chloride, ethyl n-butyl bromide means. So that when those are combined together, mixed products will get it. Already previously we discussed, once see that video. And methyl bromide, n-propyl bromide also mixed alkanes will get it. Ethyl bromide, n-butyl bromide also mixed alkanes will get in. But N-propyl bromide, we don't get mixed alkane. Only one alkane will get it. That is N-hexane. Okay. Next, N-methyl butane. Sorry. Okay. Here, what is a 2-methyl butane? See, once your structure was given, here 2-methyl butane means this one. This 2-methyl butane, when it is undergoing bromination, when it is on reaction with bromine in the presence of sunlight. What is happening? Bromine in the presence of sunlight. Very important. Bromination is selective. Bromination is selective. Selectivity. So that's why bromine directly will go towards stable radical. Which is stable radicals? Tertiary radical is stable. That's why it will attack at this position. Why means here when hydrogen is replaced by bromine. So when hydrogen is going out, there will get tertiary radical. That tertiary radical is combined with bromine radical. Like that. So which substance we will get it here? 2-methyl butane on reacting with the bromine in the presence of sunlight. There you will get it. Hmm, there we are getting 2 bromo, 2 bromo, 2 methyl. What you will get it? 2 bromo, 2 methyl butane we are getting. 2 bromo, 2 methyl butane. Okay, he's of substitution of hydrogen atom. That means which hydrogen we can easily remove from alkane means from tertiary carbon. First we can easily remove hydrogen. Next secondary. After that primary. So this is what is that here? Ease of substitution of hydrogen atom is like this. Okay, so this one. Next. Which of the following alkyl bromides may be used for the synthesis of 2,3 dimethyl butane by Wurtz reaction? So, one see that 2,3 dimethyl butane. 1, 2, 3, 4, 2,3 dimethyl butane. Wurtz reaction means it is also symmetrical alkane. We can cut this one into two equal parts. Symmetrical alkane. Here we can put halogen, here also you can put. So which substance you can get to get this one? Here this and here, like this, two things you can take. That means, what is the name of the substance here? Isopropyl chloride. The substance compound name is isopropyl chloride or okay bromide you can take in. So which substance we can take in? Isopropyl bromide mean this is we have to take. Hmm. Understand? So to get 2,3 dimethyl butane by Wood's reaction, which reaction we have to take in? Isopropyl chloride in the presence of sodium metal and dry ether. In the presence of sodium metal and dry ether, we have to take it. Okay, students, these are the some of the important questions for this substance. Now, okay, that total reactions, whatever reactions are there. So, preparation. These all are preparations of alkanes, and these are chemical properties. Just I will brief that one. Here, chemical properties of alkanes. See once. Here, okay, Sebastien-Sandens reaction. So alkyne. This is alkyne is converted into R bond CH2 bond CH3. So alkyne is converted into alkane, and alkene also converted into alkane. That means here multiple bonds converted into single bond. That reaction is called Sebastien-Sandens reaction. Next, see alkyl halides. Alkyl halide, when it is reacted zinc copper couple, concentrate HCl, red phosphorus Hi, lithium aluminum hydride, then halogen is replaced by hydrogen. R bond H you are getting. And this is what is that alkyl halide, sodium diether reaction. Their halogen is replaced by another alkyl, R1, R dash. Like that alkane, higher alkane we are preparing. And next, Franklin reaction. This Franklin reaction, if you take in, so this alkyl halide, when it is reacted with zinc metal, Franklin reaction, that X is replaced by another alkyl group. So R bond R. So higher alkanes we are getting. And Corey House synthesis also, that halide is replaced by another alkyl group, R bond R dash. So like that, from these all groups, from these, okay, 2 to 5, the first case only, okay, lower alkane we are getting same number carbon, remaining three cases higher alkane we are getting, higher alkanes we are getting. Okay, next, here alcohols, aldehydes and keto groups and acyl alkyl groups and acetic acid, when the presence of red phosphorus charge, these all will be converted into alkene. These all will be converted into alkane. Next, keto group and aldehydes. Sorry, here both are keto group is given. Aldehydes and ketones in the presence of Clemmensen reduction and Wolff-Kishner reduction converted into alkenes. Converted into what is that here? R bond CH2R. Like that, both are giving alkenes. Both are giving alkenes. Next, hydroboration. In this hydroboration, what is the R bond CH2 bond CH2 bond H you are getting in the presence of water and protonation H plus. Okay, yes, sodium alkanoate. Here, this NaOH is what is our soda lime. NaOH is soda lime. Decarboxylation is taking place. Decarboxylation is taking place. In this decarboxylation, what's happening there? So there we are getting that R bond H. So like that alkanes we are getting. What you got it there? Alkane decarboxylation. The Kolb's electrolysis. What you got it? R bond R you got it. Higher alkane. R bond R. So like that. So this side whatever is given, all are example for what is that? Preparation of alkanes. Preparation of alkanes. Already this total hydrocarbons part 1, part 2, part 3, what we discussed, these are on. Next, chemical properties. Chemical properties means what is the halogenation. So here alkane. Alkane, whenever you're taking, this hydrogen is replaced by halogenation means halide. So R bond X you are getting. Here nitration means alkyl. Alkane, when you take it, hydrogen is replaced by NO2 group. And sulfonation meaning what is the alkane when you take in? So here H2S2O3 means what is that volume. This volume, when it is reactive with alkane, there sulfonic acid you are getting R bond SO3H. H is replaced by SO3H. And this is Reed's reaction. Just now we discussed R bond H is converted into R bond SO2Cl. Alkyl sulfonyl chloride will get it. And this reaction is what is the isomerization. So N-butane when you take in, it's converted into its branched chain. So isobutane. Hmm. And pyrolysis if you take in, so N-hexane, one long chain if you take in, it's converted into small chains, propane and like that, propanes like that. That means one bulky, one long chain converted to simple chain that is called pyrolysis or cracking. And next, this is what is an aromatization. Aromatization. In this case, N-hexane, if you take in, what you will get it here? It's converted into its aromatic compound like benzene ring. It's converted into benzene ring. Okay, students. And next, alkane, when it is reacted with diazomethane, so sorry, it is not alkyl halide here. Alkane, when it is having diazomethane, R bond CH, like that, higher alkane. Higher alkane, R bond CH3 plus nitrogen gas you are getting. And last one is alkane when it is under combustion in the presence of light. There you are getting carbon dioxide and H2O. Okay, students, like that it is briefly I explained the total reactions chart of alkanes. Okay, thank you. Thank you very much.